All right, so we're going to go over the related rates notes, everyone's favorite. So the big idea here is the derivatives that we're going to be taking are going to be functions of time instead of like y being a function of x. And so that's going to lead us into weird derivatives. So like in this one, instead of saying dy dx, I'd say dy dt if I took it, since it's a function of time. So x is kind of like also a function of time, and so because of that, when we take this derivative, the derivative of y on its own is just 1, but then a dy d whatever it's a function of pops out, so dt pops out. Same thing with this kind of thing. Our normal derivative would be 2x, but then a dx dt pops out. Now, I do not prefer this language. I prefer, instead of dy dt, I prefer y prime, and instead of dx dt, I prefer x prime. That's because it's less writing, and less writing is wonderful. So that's one of our derivatives. I wasn't really reading the whole question. I just got distracted and started talking about that. Go me. So it says find dy dt. So we want to know y prime when x is 1. So one of the biggest issues that people run into here is they see x is 1, and at the very beginning they'll go, oh, x is 1, and they'll plug it in. But if we do that and we go and we plug that in, it says y is equal to 4. And what this is saying is x is 1 and y is 4. And we almost go, oh, so x is always 1 and y is always 4. And it's like, no, they're changing over time. And so because of that, like these numbers are useful, but not right now. We can use these later. It says when x is equal to 1. So this is something we want to plug in later. It says dx dt is equal to 2. So that means that x is changing, and the rate that it's changing is 2. So now if we come back over here to this derivative, we can say, well, y is changing at some rate, and that rate is dependent on whatever 2 times x prime is. And this is where we say, okay, well, at this instant, x is 1 that we care about. And at that instant, the rate of change of x is 2. And so we can get an answer of 4. So that's our first problem. So let's move into the next one. All right. Oh, I wonder if me using marker. Oh yeah, marker's gonna be bad. Let me switch to a different writing utensil. Okay, so I found another writing utensil. Suppose x and y are both differentiable functions of t. Okay, so again, it's just saying, yeah, instead of being d something dx, it's going to be dt. So let's take this derivative. Again, I'm not even going to read the question. I know I'm probably going to have to take that derivative. So the right-hand side's the easy side. It's just 3 dx dt. But the left-hand side, we're going to have to use the product rule. So I'm going to take the derivative of the first one first. So 2 dx dt y. That's the only thing I took the derivative of. Everything else just chilled. Plus 2x, and I'll take the second derivative. But again, this notation is a little bit clunky, and it might be a little bit easier to do to x prime. I'm using marker again. Oh well. Plus 2x y prime is equal to 3 x prime. So if we look at that, and let's see, I want to find dy dt, I want to find y prime. So I really want to get this over to the other side. So if I do that, so now I've got 2xy prime over here. I've got my 3x prime minus 2x prime y. I'm trying to get y prime all alone, so I'll divide both sides by 2x. And so we'll get y prime is equal to whatever this mess is. And let's see. I know 3 is that. I know that's that. 2 is still 2, x prime is still 3, and then it asks me for y. Oh, we don't know y, but we know that. So we'll have to find y. All right, 2xy is equal to 3x. We do know that at this instant, x is negative 2, so I'm going to say 2 times negative 2, y is equal to 3 times negative 2, and get negative 4y is equal to negative 6, and get y is equal to 6 over 4, which is 3/2, and then the rest is arithmetic, so go for it. All right, so now we get into real world stuff. All right, it says a pebble is dropped into a pool causing ripples in the form of concentric circles. All right, just like a real rock when it falls in the water. It says the radius of the outer ripple is changing at a constant rate of 2 feet per second. So if we're thinking about that, hits the water, and then we get these circles, and the circles are going to grow bigger and bigger and bigger and bigger. And so it says the radius is growing at a constant rate of 2 feet per second. So I could really think about that as r prime is equal to 2. At what rate is the total area changing when r is equal to 4? So we want area prime when r is 4. And I like using that as kind of a keyword to myself to remind myself that 4 is only at this specific moment in time, because r is only going to be 4 for a brief moment. Okay, so if I think about the area of a circle, that's area is equal to pi r squared. And so if we were to take that derivative, we get 2 pi r prime. Because the 2 comes down. And the important thing to remember here is that pi out front, that's not a variable. That's a number. So if I took the derivative of pi, that number, you would just get 0. So if I hop in here and let's see, well, r prime is 2 and r is 4. Oh, 2 pi 4 2. It is literally that simple. 2 times pi times 4 times 2. 2 times 4 is 8 times 2. Okay, 16 pi. And we may not leave it like this, because we were given units and we need to make sure we use those units. So let's see, feet and seconds, but it says area, so area is feet squared, so boom, there we go. Okie doke. So now we start getting into these real world scenarios. Feel free to leave any questions below, or Schoology message me or email, or talk to me in person like a human being, whatever you want to do. All right, air's being pumped into a spherical balloon. Okay, because those totally exist. Ooh, it's a spherical balloon at the rate of 4.5 inches cubed. So, I definitely kind of skipped over this in class. Air being pumped in, inches cubed per minute. This might not be immediately apparent, but that is a volume. So this is a V prime right here. Find the rate of change of the radius. That's r prime, right? When the radius is 2. So we have our when r is equal to 2. We want r prime when r is 2. Okay, so this is actually, again, it's going to be pretty simple if we know our volume equation. And since it's a three-dimensional volume, we're thankfully given this equation. And we can just do V prime is equal to, well, 4. Those are just numbers. That's a number. So we can bring the 3 out front. And then make sure to have the r prime pop out at the end. So we do that, and yeah. Oh, 3 divided by 3 cancels. So we have V prime is equal to 4 pi r squared r prime. And if we look here, well, we know r is 2. Oh, and we know our v prime. The only thing we don't know is r prime. So in class, I kind of emphasized that the way that we want to solve these is we want to divide both sides, or sorry, we want to solve for whatever we're looking for before we start plugging things in. It can save you kind of screwing things up and make you look smarter. So all I have to do now is go and find the numbers. Well, there's that one. There's that one, there's that one, and then that one's that one. So if I'm going to type this into my calculator, I'll do 4.5 divided by, and make sure you put this in parentheses, otherwise it's going to mess up. 4 times 4. Okay. Bap. I got gross. So, leaving it like that might actually be nicer in this situation. 0.895. I went one more decimal place than I had to. Go me. All right, and that's going to be inches per minute. And let me just make sure. It says we wanted r prime, which is a length, and so I don't need any squared or cubed there. And we've got that one. All right.